So we just have. I'm just going to copy the problem, so I'm not missing much. Consumer chooses X1, X2, Xn. I gotta maximize the sum AI. Before I continue, is everyone comfortable with the summation sign? I can do it in I can just write all the terms. For me, it doesn't matter. So, but this is obviously just less to write. So is everyone okay with the summation sign? Everyone understand? Okay with it? Cool. Okay, so we have this subject to the budget constraint, or something that looks like a budget constraint. AI positive, PI positive, solve Lagrangian, and we get a hint. Okay. So this is the problem for part A. I'm just gonna set up the Lagrangian. Okay, and I'm gonna take the partials. Again, if somebody wants me to just write it as sums, just let me know. The derivatives is just AI times 1 over xi minus lambda pi is equal to 0. And then you just have the lambda derivative, which is just the budget constraint. Cool. These are all my conditions. And now if you're stuck, we should have just used the hint, which is, I think, express xi pi in terms of lambda. So I'm going to work in this equation over here. And what I'm going to do is AI over xi is equal to lambda pi, which is equivalent to AI is equal to lambda xi times pi. I moved the xi on the other side. And now I'm going to move the lambda on this side. So this is just equivalent to AI over lambda is equal to xi pi. Okay. One thing that you needed, well, not necessarily needed, but it's good habit to make talk about is, in this case, I divided by lambda, right? So if I'm dividing by lambda, I'm automatically assuming it's not equal to 0, which I have no information about. So it's good to just make like a one-line argument saying something like lambda can't be 0 because then from the first equation, from the partial, let's put this one, then from 1, I would get AI over xi is equal to 0, which is impossible. Okay, so it's good to just have this sort of argument always in your in your sleeve. Now I have this equation, and all that I'm gonna do with it, I'm just gonna replace my PIXI from the budget constraint with this. So my budget constraint was P1 x1 plus P2 x2 plus dot 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 plus Pn xn is equal to M. And I'm just going to replace this with A1 over lambda plus A2 over lambda plus dot 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 An over lambda is equal to M. Okay. Now I'm just going to try to leave this here so we can still see it. Yeah, so I'm still have that equation, which is just the same as writing A1 plus A2 plus AN over lambda is equal to M. So sum of AI's I from 1 to N over lambda is equal to M. So lambda is equal to sum of AI I from 1 to N over M. Now, some questions that I got and I forgot to address, I guess, is why is the problem not done when you're here? Is because you don't know lambda and you don't know xi. So you technically have not solved the problem. You need to actually give me xi in terms of something that I can compute. So this lambda I can compute, because if the problem, I don't know what's wrong with the camera. If the problem wanted me to give a numerical solution, like if they wanted me to tell you what xi is, they would let me know what AI is, what M is. So in this case, I could just tell you if they give me the values, lambda is equal to 0.2 or something. But I'm just going to take my lambda and plug it into my AI over lambda is equal to xi pi. I'm just going to take my lambda and put it here. So AI over, and I'm going to copy it, and then I'm going to make a small adjustment just so it's clear for everyone. 1 to N over M is equal to xi pi. I've seen people simplify AI with AI, which is completely wrong. So in order to circumvent this or just make it not as close, I'm going to change the notation here. Instead of sum from I, I'm going to say sum from K, just because it looks so much more different. Okay, just so you're not tempted to simplify, which would be a huge mistake. So xi is just equal to 1 over pi times AI times M over sum K from 1 to N AK. Okay, and the problem is done right now. The first one at least. Looks fine. Cool. Any questions on this? Cool. Then problem number B says state the Cantucker conditions for the original problem with an equality constraint. Okay, blah blah blah. Good. I think I got it. So they're giving me this new condition, x1 greater or equal to 1. And they're actually giving me the hints in which they're saying the equation might need to be reorganized. The argument is that you don't know how to work with these type of inequalities. So I'm just gonna multiply everything with a -1. And I'm gonna get minus x1 smaller or equal to -1. Just so I get this. That's the only reason. Now I'm gonna write the Lagrangian. The Lagrangian is the same original thing, sum from I equals 1 to N AI ln xi minus lambda sum of pi xi I from 1 to N minus M. And now I gotta add in the new constraint. So the way to do that is basically just putting another lambda. I don't care if you put it mu or whatever. I am more comfortable with lambda myself, so I'm just gonna go with what I'm comfortable with. But if you put mu or anything else, I don't care. For me, I'm just gonna put lambda 1 here minus lambda 2. and I get minus x1 plus 1. Okay. Now, when I write the partials, it's important to note that specifically the partial of L with respect to x1 is different than the others. Why is that? Because I still will have a1 times 1 over x1 minus lambda 1 times p1, but I also need to take a derivative of this with respect to x1, which is going to give me minus lambda 2 minus x1 is equal to 0. Okay. All the others, derivative xi, I greater or equal to 2, are going to be exactly the same as in point A. Yeah.
Isn't it plus lambda 2?
Yeah, I said it is plus lambda 2, but I put minus lambda 2 minus x1.
Yeah, the derivative of the function with respect to x1.
I ask. Yeah. So. Oh, yeah. So. What did I?
The x1 way since it's a linear.
Oh, yes, of course. Oh, sorry. Yeah, I forgot to take a derivative of it. Yeah, that's if that's what he meant. It's just minus 1 here. Yeah. Okay. Yeah. Exactly. I said I'm going to take a derivative, but I didn't take a derivative. Okay. Yeah. No, it's times minus 1 there. Because when I take derivative of x1, it just goes away. Of course, I didn't take a derivative of it. Okay. Now, one thing that I have to write here is the derivative of L with respect to lambda 1, which is just going to give me this pi xi I from 1 to n minus m is equal to 0. Now, it is wrong to write derivative of L with respect to lambda 2. This is wrong because if I were to do the computation, I would just get x1 equals 1, which is wrong. So this is wrong. On the other hand, I'm just going to write the Tucker conditions or the complementary slackness or however you want to call them. This is something else. And the way it goes is, okay, if first case, if I have x1 strictly, let's put equal first. Why not? If x1 is equal to 1, then lambda 2. Again, I have no information. Tucker tells me nothing about lambda 1. It only talks about lambda 2, the new constraint, because I have only one inequality, right? Only this inequality. The budget constraint is with equality. So I'm writing the Tucker only for this lambda 2. x1 is equal to 1, lambda 2 has to be greater or equal to 0. And secondly, if x1 is strictly greater than 1, then lambda 2 is equal to 0. Okay, everyone okay with that? Cool. Now I'm gonna check again what's the next problem. So they basically just gave you the complementary slackness conditions. Okay, sure. Sure. So they're asking us to solve it, to solve the Tucker, basically just saying, okay, they're basically just asking us to solve it, saying something like, okay, what happens if x1 is equal to 1? And here's the thing. The inequality is so not trivial, but it's so direct that if x1 is equal to 1, x1 is no longer a variable of interest, right? Like x1 is fixed. So I don't really need to worry about this anymore. In the sense that my problem now, if x1 is equal to 1, I can't choose x1 anymore. Okay, I can't just pretend that I'm maximizing a problem over x1 when I know x1 is 1. It just doesn't make sense. So the problem that I have to solve is, I'll rewrite it again. I have to maximize this. That's my problem. I have to maximize sum from I equals 2 AI ln of xi to n. So I just have to maximize the utility I get from the other goods, subject to a budget constraint. Okay, what is this budget constraint? Is it still M? Is this still M? Again, notice, really important, I only put from I equals 2 onward, because my argument is x1 is not a variable anymore, it's a fixed constant. So is this correct? Am I still maximizing across the same budget? The answer is no. Since I'm basically fixing this x1, I'm out of my budget, I'm spending enough money to buy one piece of x1. So the correct thing is I am maximizing the utility I get from all the others, subject to the budget constraint being equal to what's left after buying one piece of x1. How much is left after buying one piece of x1? It's just m minus 1 times p1. Okay, this is how much I spent. How much I spent on x1 is equal to 1. Okay. Now, does this make sense to everyone? Is it clear? Why am I doing this? Because now, if we just go back to the first line I wrote, and I'm going to ask you, does this problem look familiar to this problem? Because for me, they kind of look almost exactly the same, right? So my argument now is, why should I just solve this thing again when I basically just solved it in point A? So I'm not going to solve it. I'm just going to say from point A, I know that the solutions to this are xi for I greater or equal to 2. Xi is equal to, and I'm just going to copy stuff if I find the solution somewhere. Oh, here. It's just equal to this. So let's almost equal to that. Let's be careful when we write it. Okay, so let's write it carefully and slow. Xi is equal to 1 pi times AI times, I don't have m anymore. So instead of m, oh, we can't see it. Like this. I don't have m anymore. Instead of m, I have m minus p1. So m minus p1. And underneath here, I don't have sum from 1 to n. I just have sum from k equals 2 to n of ak. Okay, and I'm done. Any questions here? No, this is kind of a good example for work smarter, not harder. No, it wasn't the other way around. Never mind. Anyway, yeah, so the idea is, if you just notice that you're basically just solving the same exact problem again with just this m minus p1 instead of m, you could just take the results from A. That was how the problem was intended to be done. Now, problem D, consider the case where inequality constraint is equal to 0. What is the optimal solution? Okay. So let's do problem D. Problem D, I know x1 is strictly greater than 1. And from the Kahn-Tucker, I know that if this happens, my lambda 2 is equal to 0. So let's go back to my budget, to my where did I put it? Let's go back to my Lagrangian conditions. If I could find them, that would be absolutely great. Okay, found them right here. Okay, let's look here. These are the problems. All that I'm going to do right now is I'm going to replace lambda 2 is equal to 0. That's the only thing I know. That's the only thing I'm going to do. Okay. So where's the only place that I have a lambda 2? Right here. That's my lambda 2. So if that's 0, then I can just cut it out. Okay. Now, just looking at these relationships over here, I notice now that after removing this part, after just erasing this lambda 2 thing, the condition for 1 is the same as the condition for I greater or equal than 2, right? Exactly the same. And again, it looks very much exactly like the problem in A. Right, exactly the same conditions, right? So in this case, again, I don't need to solve anything. If this happens, then from A, I know that xi is just equal to, and now I can just copy because it's exactly the same. I mean, I'll just copy it from here. I don't need to show that. Oh, yeah. M sum k equals 1 to n ak. Cool. So again, the argument why I can do this is because, okay, x1 is greater than 1. It's strict. So from the Kahn-Tucker, I know lambda 2 is equal to 0. I take this lambda 2 equal to 0, and I go to my partial equations from the Lagrangian, and I just plug in lambda 2 is equal to 0. So there's only one lambda 2, which is here, so I can basically just remove this thing away. And now I have the same equation for x1 and for all the other x's, which are the same exact equations that I had in part A. Same exact equations. Equation 1, this is equation 1, and this is now equation 1 as well. And the budget constraint is exactly the same. Again, budget constraint here, budget constraint here. So having this in mind, then it means that my optimal choices for the consumption are just the same. Okay. If I were to solve it, if you know, it makes sense in the sense that I have the same equations, the same constraints. Obviously, if I solve it, I'm going to get the same solution. Okay. Now, point E, does the solution satisfy sufficient condition for a maximum? And now they give you the hint here. You use the fact that a sum of concave functions is concave. Or if you're still stuck, simplify to n equals 2. Realistically, I think if you attempt to simplify to n equals 2, it's actually way more work than using the first one. So let's just do point E right now. The condition that they're asking for is basically showing that the Lagrangian is concave. Okay, let's see. Let's look at our Lagrangian. Honestly, it doesn't matter which one we look at. So this one I think is nicer, much nicer written. So let's look here. This is my Lagrangian. If I'm looking for convexity, if I'm looking for convexity or concavity or something, or that sort of thing, what should I usually look at? The second derivative, right? That tells me if it's positive, it's convex. If it's negative, it's concave. Now, it gets much more complicated when you have two variables because you got to use the Hessian. And when you get n variables, you still have to use the Hessian, just that you have exponentially more terms. So computing straightforward is not an option. Unless you take n equals 2, which is fine. Computing for n, even n free, might take you a while. And I'm not convinced you know how to do it. So let's just take the hint. My first observation is that it's not a smart observation, I know, but it helps, it builds up, is that this thing over here, minus lambda 2 x1 plus 1, whatever, that's a linear equation. Do you guys agree? It's linear in x1. Okay. Same for this thing. It's linear. So a linear equation, if I take two derivatives of it, it just goes to 0. So when it's linear, it's not going to affect your convexity. That's not going to be the problem. The problem is this first part. That's going to tell me whether or not the Lagrangian is convex or not, the first part. And the hint basically tells us that a sum of concave functions is concave. So let me try and write this Lagrangian in a way that maybe makes a little bit more sense. I'm going to write the Lagrangian as let's write it like this. So this is not necessary. I'm writing way more steps than I should have, but this is just for you to understand. I'm not expecting you to do this on the exam. Like on the exam, I'll emphasize you probably only need the 2 lines I'll write at the end. But the idea is that I can just write A1 ln of x1 minus lambda 1 p1 x1 minus, what was it, lambda 2 minus x1 plus 1. Okay? Plus a2 ln of x2 minus lambda 2 or lambda 1 p2 x2. Plus a3 ln of x3 minus lambda 1 p3 x3 plus dot 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 an ln of xn minus lambda 1 pn xn, and just put at the end minus lambda minus n. Okay. The reason I wrote it like this. So, first of all, does everyone agree that this is the same Lagrangian as before? This is the same Lagrangian as this? Is everyone kind of on board with that? Why is it the same? Well, basically, this column is just sum of AI ln of xi. This column is just the budget constraint, and this column is just the final thing I added. Okay, so everyone on board that it's the same thing. Cool. Now, the idea is that if I can show that each of these things is concave, each of these lines, each of these rows is concave, like for this is concave, this is concave, this is concave, then I'm just going to use the property that a sum of concave functions is a concave function. That's my whole thought process. So what's the benefit of this? The benefit is that on these lines, I only have one variable. So I only have an x1 here, x2, x3, x whatever. So I can just do a double derivative on one variable, which shouldn't be that hard. So let's just take derivative of the first line, a ln x1 minus lambda 1 p1 x1. Okay, derivative with respect to x1. Yeah, I'm sorry, guys. My neck still hurts a lot. Okay, this is just equal to a1 times 1 x1 minus lambda 1 p1 plus lambda 2. Okay, and now I'll take derivative again because I need to take the double derivative, right, in order to see if it's concave or not. And this goes away, this goes away. This is just minus a1 over 1 x1 squared, which is just going to give me, which is just smaller than 0. This is positive. There's a minus in front, and x1 squared is greater or equal to 0. So this is negative. So this function is concave, clearly.
Really, the parenthesis that
Where?
the
Oh, like this?
yes,
Yeah, 100%. If I wanted to be very thorough and yeah, 100%, yeah. Yeah, okay, yeah. I need to do that as well, yeah. Sure. Okay, so now I just use what the problem tells me: a sum of concave functions is concave, and L is concave, and I'm done. Now this condition actually translates almost the same as what you've learned, which I'm not really sure exactly why you're not just using the fact that lambda 1 is greater or equal to 0. Probably because in this case you have the lambda 2, and you need to have like an understanding that that's linear and doesn't affect it. But in this case, when you have multiples, I guess it makes, especially for what you know in this class. I just made this short comment about just proving lambda 1 is positive because that usually is enough, but here you have 2 lambdas. So unless you know what you're doing, you can't just finish by saying lambda 1 is greater or equal to 0, which I would accept. I think it's an enough argument for this class. But when they give you the hint that a sum of concave functions is concave, it points towards this type of solution. Now, what were you, if you, I said on the exam, you don't need to write to show me all of this or something like that. If you just told me, if you just wrote on the exam something like literally linear, so this is linear, and then just computed derivative of, and then just computed me derivative of ai ln of xi over double derivative of xi squared, and told me that this is more than 0, that's more than enough. You don't need to show me anything else. Okay. In the remainder, suppose that n equals 3. Okay. Now we're back to some of your favorite parts, which is basically we're just going to plug in numbers. And I am not going to compute any of this, but I will try to approximate them just so we see which one is the correct answer. I will not be using a calculator. In this case, see, I hate calculators, but in general, but in this case, like specifically in this problem, I think if you had a calculator and you're not that good at approximating, then it's probably good to use it. Okay, this is one of the only cases where I would say that a computer is useful. Will you actually have a problem like this on the exam? Around 1% chance or less. So I still don't think you need a calculator, but it's good that you have one. So if M is 12, what is the optimal solution? Is the quality constraint binding? So F M is equal to 12, and that's 6. Okay. So why are they asking us what's the solution, et cetera, et cetera? Remember, when you're splitting in the Kahn-Tucker, you're basically looking at two potential solutions. In most of the problems that we've done, one of these cases didn't have a solution, so there was nothing to compare it to. But what they're basically asking us to do in this problem is just compute both solutions and then see which one is bigger. Okay, so that's what I'm going to do. I'm just going to use the formulas. So let me show you how I'm going to do it. Oops. So in the case that x1 is equal to 1, then m minus p1 is just equal to 9. And now I can just apply the formula that I wrote in point C, which is that x2 is going to be equal to 1 over p2, which is 2, times AI, which is 1, times mp1, which is 9, over, what's this, 2. X3 is just equal to 1 over 1 times 1 over 9. I'm just literally I'm just, in case you think I'm writing stuff that comes to my mind, I'm basically just using this formula over here and plugging the numbers in. Okay, that's all that I'm doing. Hopefully I'm plugging them correctly, but you never know, really. So this is just the n over 4, this is just n over 2, and x1 is equal to 1. So this is in the first case. In the second case, x1 is just equal to 1 over 3 times 12 over 3. X2 is just equal to 1 over 2 times 12 over 3. X3 is just equal to, what is this? Right, 1 over 1 times 12 over 3. So this is just 12 over 9, 12 over 6, and this is just 12 over 3. Now, my brain hurts. Now, what you have to do is just plug these x1s into your formula, which was sum of AI ln of xi, which in our case is basically just ln of x1 plus ln of x2 plus ln of x3. And ideally, you would just plug and see what you get. Since I am quite terrible at, I said I'm not going to use a calculator, and I think I can approximate ln the way it goes decent. I'm going to say that if you were to plug them, the correct answer here is this one. That would be my guess. That would be my guess right now. Let me 1 sec. Yeah, I think I'm quite confident. I think it's correct. Correct. I don't know if you plugged it at home or something, but if you want to do it in the break and prove me wrong, hopefully I'm not wrong, but that's what I think. I'm fairly confident if you just plug these values in, you're gonna get double I bigger than I, which would imply that I got this constraint, I got x1 12/9, which is greater than 1. So they're asking me, is the constraint binding? No, the constraint is not binding. Okay. And now just finish up with doing G. Where I had m is equal to 6, m is equal to 6, and let me think. I x1 is equal to 1, m minus p1 is equal to 3, and I get x2 is equal to 1/2 times 3/2, that's 3/4, and x3 is equal to 1/1 times 3/2. This is 3/2. And then double I is just equal to x1 is just equal to 1/3 times 12/3. That's 6, of course, 6, because my budget changed, which is just 2/3. And then x2 is equal to 1/2 times 6/3, which is just 1, and x3 is just 1 6/3. This is just 2. And now if you plug the numbers, I can tell you I'm fairly 99.9 sure that I is going to be bigger. Yeah, much bigger. So I'm going to say that I is going to be bigger than double I. So is the constraint binding? I have equality there. So yes, constraint is binding. Cool. Now I think we should take a 10-minute break and then we'll finish up with the last problem. Okay, let's just finish with the last problem right now. Let me just copy it. F of x y is 5xy minus xa y8 y to the power of a minus 4, a greater than 1, xy greater than 0. Partial derivatives of the first and second order. Sure. Okay. Before I even started, or before I even start a problem, I guess I immediately just saw that this function is weird. Okay. In the sense that I can just write it as f of xy is equal to 5xy minus xy to the power of a minus 4. So I immediately saw the main idea, the whole point of this entire problem, just by taking 1 minute before I do the derivatives to look at the functions. That's why I always tell you before you actually go into the, not necessarily monkey computation, but basically just all the methods that are hard forced into you. It's best to just spend 30 seconds, 1 minute, look at the function, see if you actually find something that might help you down the road. So for me, I saw this, which basically says that the function does not depend on X and Y. It just depends on their product, right? And that's why whenever you guys ask me in sessions or something, what's the idea? I always replied by saying, okay, which is bigger, f of 110 or f of 5.2? Okay, and that's the idea, that their product is the same. So if I were to plug the values here and here, I would get 10 either way. And I'm always gonna dive deeper into this when we actually need it, I think, which is point C especially and onwards. But that's why I'm emphasizing it's always good to spend 30 seconds before you go into the method you know is going to give you the solution, just to see the function, see if there's anything special with it. Because in most of the cases, there is going to be something that's going to make your life easier or harder, depending if you see it or not. But for the derivatives, I don't think this should be a challenge at this point. So I'm going to compute f prime of x with respect to xy, just taking the derivative, 5y minus a x to the a minus 1, y to the a f prime of y, just 5x x a times y to the a minus 1. Double derivative of x is just, this is 0 minus a minus 1, x to the a minus 2, y to the power of a, f double y xy is equal to minus a minus 1. Oh, let's just keep the with the writing. X to the power of a minus 1. Okay. And now the derivative xy, just take this derivative with respect to y, and I get 5 minus a x a minus 1 a y a minus 1. Okay, derivatives pretty standard. I hope this wasn't an issue for anyone. Okay. Now the next point asks us to compute stationary points. How do you compute stationary points? You just make the first derivative be equal to 0. So I'm just going to make this equal to 0 and this equal to 0. Before solving it or claiming it's impossible or something, you need to show some work or do some simplifications. For me, before I start computing, and especially if I know it looks like something quite ugly and I need to do some computation, and it's especially a long computation, I want to simplify it as much as possible. So my idea is, these equations, they look, I mean, for me, they look fine, but I assume for some of you, they look quite ugly. So my first idea, since I know that x and y are not 0, the problem tells me they're strictly greater than 0. My first thing is let's just divide this by y, and let's just divide this by x. That's my first idea. It's not much, but it's honest work, you know what I'm saying. So I'm just gonna write what I get. Dividing, I get 5 minus a x a minus 1 y a minus 1 is equal to 0. The second one, so this is the derivative of x transformed. The derivative of y transforms into 5 minus x a minus 1 a y a minus 1 is equal to 0. Now you can't complain that you don't know anymore, because I taught it myself in class, so it's not the class's fault. I told you about the counting rule, okay? The counting rule in which I talked about useful and useless equations. I have two unknowns, okay? I don't know x and I do not know y. And these two equations are, hopefully we can all agree they're the same. Right. If I just move this a here, they're the same. So I have one equation, two unknowns. It means I have one degree of freedom, which I can choose however I want. So that's why at this point, let's just say you can just say, okay, so I have 5 is equal to a x a minus 1 y a minus 1, and then let's just do it in terms of y. Y is equal to 5 over a times x to 1 minus a 1 over a minus 1, something like that, I think. So, and would an answer of type, okay, all solutions of type x 5a x 1 minus a 1 a minus 1, solutions of this type are critical points for all x greater than 0. Would this be an acceptable answer right off the bat? Yes, I think if you found most of the graders and they were, if you found some nice graders and they were in a good mood, you would probably get 10 out of 10 for this. If not, you'd probably get 8 out of 10 realistically, because you're dodging the main idea of the problem, which was the observation that I made in the start. The fact that the problem depends on x, y. The fact that the problem depends only on the product. And by giving the solution like this, you are purposely dodging that whole idea, especially after you write this. You're just purposely not choosing to observe that. So the way I would give the answer is, I see this, and I know that xy is the only thing that generates the problem. So it makes sense that the critical points are a value of xy. That's the whole idea. So I can write this 5 is equal to a times xy, everything to the a minus 1, which is equivalent to xy is equal to 5a to 1 a minus 1. Okay, and this answering that all points with product this are critical points, in my eyes makes much more sense, given that the function only depends on x on their product. Okay, now I like the fact that on problem C, they're basically just telling you, oh, you thought you could ignore this fact, the fact that the function only depends on xy. On problem C, I'm basically just slamming you in the face and I'm saying, oh, now show me that that's what's happening, okay? With a weird phrasing as well that says, show that the hyperbolas xy equals k are level curves of f, attains its maximum one of these curves, which one? Okay, so if you observe the thing about the product, and if you've done the computation like this, like this, then the problem is two lines. Basically, the lines are from here. I just write it as, okay, I'll do 3 lines. Just because we're copying this. So the 2 lines are F depends only on the product on X times Y, not X and Y. You could argue not particular values or not unique values or something like this, but for this class and for us, this is more than enough. If you wrote something like this, although the language is a little bit abusive, it's more than enough to show me that you know the idea. So F only depends on X and Y. As a result, X, Y equals K are level curves. So as a result, X, Y equals K results F of X, Y is actually just 5K minus K to the power of A minus 4. So these are level curves, so it's done. And the point computed, the critical point is from B. K is equal to 5A 1A minus 1. The only question I have to answer, and the only reason I actually said 3 lines, which, I'm writing a lot of text here, but is that I have to show that this point is a maximum or a minimum. That's the only reason why I have to write an extra line or 2 lines. Because I've shown that this point is a critical point, right? Or a stationary point or whatever. But I have not shown if it's a maximum or a minimum. So how do I show that it's a maximum or a minimum? Easiest. Some of you may say, oh, you just use the AB rule here. And I agree, sure. You can use the AB rule. I think it would be quite smart. But in this case, it's a lot of work. So in my case, instead of showing that f of x, y is concave using the AB rule, I'm going to show that this function over here that basically gets the same values as that function is concave. Why would I want to show that this one is concave and not the 2 variable one? Because this is a 1 variable function. This is a 2 variable function. So that's the whole difference. I am taking a double derivative of a 1 variable function, which for me is always better. Okay, that's my idea. So I'm just going to do derivative f of k with respect to k. We'll do it twice, straightforward. So I get 0 minus a minus 1, k to the power of a minus 2. That is the double derivative. And they tell me a is greater than 1, so this is greater than 0, greater than 0, greater than 0, negative, so it's smaller than 0, so it's concave. No, there's absolutely nothing wrong if you did the AB rule here. ABC rule, whatever it's called, I don't know. In order to get whether or not it's a maximum or a saddle or et cetera, et cetera. or get the convexity out. I just I'm more of a fan of simpler problems, so I just solve the simpler version. Okay. In the end, it depends what you think your skill set is. My skill set is basically just observing from a complicated problem, just observing an easy way out. And I would rather just spend more time finding an easy way out than do a lot of computation. But if you are confident that you're good with computation and everything, just send the computation. Okay. You're not going to get premium points for solving it shorter or something like that. Now, problem number D, suppose C greater than 0, find blah. Okay. All right. C is greater than 0. Find H of Z is 5Z. What am I looking? ZA minus C is equal to 0. Two solutions, etc. And the problem tells you make a figure, is it concave, convex, etc., etc. So this function is clearly concave. I basically just showed that over here. Another benefit of doing it like this is concave. I don't need to prove it again. So it looks like this. Okay, that is what concave functions look like. Now, you're asking me whether or not I have one solution, two solutions, or no solutions. What does it mean for a function to have a solution? It basically means that the graph of the function has to touch the OX axis. Okay, so what do I mean by that? If I have this happy function over here, once it touches this point, that point corresponds to some value x that has f of x equal to 0. Right? There's just graphing 101. So basically, when the graph of a function touches the OX axis, I have a solution. Now, if the shape of my graph is like this, how can it touch the OX axis? Well, first of all, it can be like this. Okay. Which is it's just too small. It's always negative, so it never just reaches the zero axis. It can be like this, where it just touches it once. That's supposed to be 1 point. And then the last case is where it's just very big. It just goes like this. Okay. And in this case, I have two solutions. Any questions on this? Does this make sense? So again, if it's concave, we all agree that the graph looks like this. And then the second observation is that a function is equal to 0 when it touches the OX axis. So my only concern there then is seeing when this concave graph touches the OX axis. And I have no idea in which case I'm in, but I know it has to be one of these three. It's either down below, in which case it never touches it. It either touches it in 1 point, or it's just above and it touches, and you have two solutions. That's the whole idea of the problem. And now we're literally done. We're one line away. I just have one question for you guys, and that's the only thing we need to establish is how do I know in which of these cases I'm in? Okay. What tells me if I'm above, below, on the line? What tells me in which case I'm in? And the answer is you have to look at the maximum of the function. Okay, the maximum of this concave thing. Where is the maximum? The maximum is here, the tip of it, right? That's if we have a concave function, the maximum is at the top. So my argument is like this. My argument sounds like this. If the maximum of my h is below 0, then I get no solutions. If the maximum of this h is equal to 0, then I get one solution. Right? If it just touches it there, if it's just tangent to the thing on top, I have one solution. And if this max of h is greater than 0, so if my maximum is here above, then I get two solutions. This is the max. Did everyone follow that argument? Did that make sense for everyone? So I'm basically just in order to tell in which of these cases I'm in, I am just looking at the maximum that this this function can attain. Since it's a convex, the maximum is going to be obtained up top. So now I'm just comparing how the maximum is with the OX line. And if the maximum is smaller than 0, so if it's below 0, I'm in this case, so I get no solution. So this would be, if I were to label them 1, 2, 3, this is case 1, this is case 2, this is case 3. So if the maximum is below 0, then I'm in case 1 and I get no solution. If the maximum is equal to 0, or it's just tangent, I have one solution, case 2. And if the maximum is greater than 0, I have two solutions, and I'm in case 3. Okay. And finally, for the cherry on top, to just finish it up, is what is my maximum? When is h maximum there? Well, I just solved it previously, right? When I computed the critical point, which was the maximum point right here. So then the last step is basically just plugging that in instead of z and seeing what the relationship is. But before I do that, I mean, I'm not even convinced I'm gonna do that, because just plugging in. I would rather just go over the arguments that got us to the solution once again. So the first argument that I came up with is the fact that the function is concave. Then I know that you get 0, or you get a solution whenever you cross the x line, the OX line. So my next step is to combine these two and see where this concave function goes. And after a little bit of thinking, I realized that I'm in one of 3 cases: the case where it's all the way down below, the case where it's tangent, and the case where it just goes above the line. And in order to see in which of the cases I am, and I just look at the maximum of it. And according to how the maximum is to 0, I can just say no solution, one solution, or two solutions. And that's basically the entire problem. Okay? Any questions on this? Okay. The only last thing, which I'm just going to write here, is that max of H happens when Z is just equal to the critical point from the previous parts. So you just have to replace this. Okay, now let's just do the last one. And we're gonna be finished in less than 2 hours. That's how long it took you guys as well, right? To solve this. Maybe a little bit less since I wrote a lot of explanations, so 30 minutes, give or take. So last part is E P and Q are positive constants. Solve the problem. Oh my God. Px plus Qy plus Qy, subject to some ugly stuff, subject to 5xy minus x squared, y squared is equal to 4. Okay, now, two ways, two comments. First of all, if you just plug in the Lagrangian right now and start solving, you can do it. Okay, you're gonna get a solution very well. I've seen some good guys computing, and their computation was not too friendly, but they got it out, so not bad, quite good. Now, you probably know me by now. I need a simpler solution than that, because taking derivative of this and then plugging it in and then getting a relationship in terms of that, kind of ugly. So let's think of doing something else there. You can. So one observation is that this looks like our main function from A, right? It looks because our main function from A, I'm going to write it down below. F of xy was just 5xy minus xa ya minus 4. So it looks kind of similar for A equals 2. So going and working with it is fine. I can believe you do that. And you can get an interesting conductor, which honestly I think is the way the problem was intended to be solved. But there's a much easier case to solve. And it has to do with the fact that this equation does not care about x and y, it cares about their product xy. So before I start, oh, you're not seeing much. Sorry about that. So before I actually start doing the Lagrangian, I'm gonna work a little bit here. Just a little bit. So I'm gonna write it as 5xy, xy to the power of 2 equals 4. And I'm gonna write it like this. So again, the whole idea here is that this problem does not depend on it does not I mean I can even okay this problem does not depend on x and y. It depends on their product. So this condition here, my constraint, is basically just giving me a constraint on their product. So why would I use this complicated looking formula when I can just use a constraint on their product, which looks much nicer? So one idea is to just say, okay, xy is equal to k, and write it as 5k minus k squared is equal to 4, and apply the delta b squared minus 4ac condition, do the computation, and get the solutions. Again, I'm not a fan of that. I can do it much easier than that myself. So I'll just write it like this. I get the same solutions, but I'll just do it like this. I'm saying 5xy is just equal to xy plus 4xy minus xy squared is equal to 4. Okay. And now you're gonna say, okay, this guy's crazy. Why did he do that? And I'm wondering myself as well. So now I'm just gonna group this with this. And I'm going to group this with this. I'm just showing you different things. This is how I would have done it. I'm just showing different methods. If you did it with the delta b squared minus 4ac, very well done. It's your solution is much more general than mine. Mine is just lazier, I guess. So I get xy 1 minus xy and then I get plus 4 xy minus 1 is equal to 0. So now I just group this with this, and I get xy minus 4 xy minus 1 is equal to 0. Okay. From here, if you have two numbers multiplying being equal to 0, it means that either the first one is 0 or the second one is 0. So I just get either xy is 4, xy is 1. Okay, and I basically just skipped the b squared minus 4ac. But these ideas that I have are just kind of thing, kind of like you either see it or you don't, unfortunately. Anyway, now which one of these constraints should I choose? Can I eliminate which one I'm working with? And in this particular case, because P and Q are positive, so P and Q are positive, so for me to minimize this thing, I would like X and Y to be as small as possible, still being greater than 0. It makes sense to say that I'm only going to consider the case where the product is the smallest. So again, my argument was like, I tried to minimize this cost. The prices are positive. So since I'm minimizing, it makes sense to take the case where the product is the smallest. If the argument was not so clear, maybe I did not know that P and Q are positive. Maybe the problem didn't tell me. Maybe they could be negative. In that case, I would just have to solve for both of the cases. Okay. In that case, I just had to say, okay, we're going to solve for this one first, and then we solve for this one, and then we see which one is better. But in this case, I can exclude the bigger version because I want to minimize. So rewriting my problem is minimizing px plus qy subject to xy is equal to 1. And this looks much better than the previous constraint. Now, in this class, you don't know how to do minimization problems, but you do know how to do maximization. So we're just gonna write it as max minus px minus qy subject to xy is equal to 1. And this is a simple Lagrangian, which I would hope everyone is more or less confident to do. I roll the Lagrangian, take a derivative with respect to x, minus p minus lambda y is equal to 0, minus q minus lambda x is equal to 0. Write the constraint as well. from here, I get lambda is equal to minus P over Y. Lambda is equal to minus Q over X. Lambda is equal everywhere. So I get P over Y is equal to Q over X. And this looks fine, I guess. I can just write it as, I don't even know. X is equal to X. Yeah, X. Sometimes these easy equations are the hardest for me. So Q times Y over P. And what do I do with this X? I just plug it in here. And I get Q times Y over P times Y is equal to 1. So Q over P times Y squared is equal to 1. Y squared is equal to P over Q. So Y is equal to square root of P over Q. There is no plus minus. It's only plus because the problem tells me that Y is positive. So no plus minus. And X is just equal to square root of Q over P. And we're done. Obviously, now you understand if I just did the other case where xy is equal to 4, then I would just have 4 here. I would just have 4 here. And I would just get 4 times these things, which would obviously not minimize my sum. I would just make it bigger. Or, 2. But anyway, that's not the case. If you want, you can just do it with plug in here 4, but you're just gonna get something worse. But yeah, this was your mandatory assignment. So any questions on it? Otherwise, this was all. Yep.